anatomists and physiologists. This is part 2 of our digestive system series. This is about the major digestive organs. We'll start by talking about the beginning of the digestive system, which remember, it's just one long tube. The beginning part is the mouth, and there's a lot of accessory structures going here, like the teeth, the tongue, all of that kind of thing, the salivary glands. And all of these things help the digestive process begin. But there is an epithelial lining. So all of the lining of the mouth is stratified squamous epithelium. So it's many, many layers of smooshed cells all stuck together pretty tightly. And that's really great in the mouth for protection because the mouth is subject to lots of scraping and friction and that kind of thing from eating. The digestive process occurring here is ingestion. So I'll write that down. So ingestion. And remember, ingestion is just eating. But then we start the process of mechanical breakdown. So ingestion includes chewing, or mechanical breakdown rather. Mechanical breakdown. And that's called mastication. Which is chewing. In the saliva, there's also an enzyme called amylase. So in the saliva, there's an enzyme called amylase. Amylase helps with starch digestion, which is a little bit of chemical digestion too going on in here. Starch is a carb or a sugar, and it's in stuff like potatoes, grains, all the delicious things in life. We'll talk more about like the mouth because there's lots of accessory structures like the tongue and the teeth and stuff for us to talk about. But after that food is masticated and then we've swallowed it, and that food that we swallow is called a bolus, then it passes through the throat. The throat is called the pharynx. It's like science for throat. And then it ends up in the esophagus. So that's where we are here. We're in the esophagus, the throat, or in the food tube. Since the esophagus is still subject to lots of friction and abrasion and stuff, what is in here is still stratified squamous epithelium. I'll highlight that for you. Stratified squamous epithelium. And this is also a really great time to point out that these are the same layers we already know from the wall. We have the mucosa, still same. Submucosa, still same. Muscularis externa, which has those two layers, the circular one and the longitudinal one. The only difference is that instead of serosa, we have the adventitia. And that's just connective tissue that sticks all of that esophagus to the surrounding structures in the thoracic cavity. Okay, so that all of these layers that I've just highlighted in pink, those are pretty ubiquitous throughout the whole of the GI tract. Adventitia, though, just gets replaced by serosa. Regardless, though, the mucosa is my point here. That stratified squamous epithelium of the esophagus. As we get closer and closer to the stomach, we change from stratified squamous epithelium because we don't need it as much anymore once we get into the stomach. Less abrasion and things. So what we're looking at here is we've taken a slice in cross-section of the esophagus. You can see a lot of these like really, really thick layers of that mucosa. And then once we get into the stomach, that stratified squamous epithelium kind of changes to simple columnar epithelium, which then is pretty much the same throughout. So here's what that process of swallowing actually looks like. And I'm going to zoom in to show you each of these phases. So there's three major phases here, and we're watching the food, the bolus, travel, and that's the green thing here. So what happens is, first is called the buccal phase. Buccal refers to like the inside of the mouth, the cheeks. Um, so what happens is that food will move down into the esophagus. So that's the buccal phase, the swallowing part. The tongue will help move and swallow that food down. After that food is swallowed, it enters, remember I told you the pharynx, right? And that's science words for throat. And notice that that esophagus is kind of sort of closed, but then as that food moves through, it starts to open, and that's the next phase there. It's called the pharyngeal esophageal phase because we're going from the throat into the pharynx, and it's still called the bolus of food there. As we move down, notice that the esophagus is closed, but it's kind of surrounding this bolus of food. And that's the process called peristalsis because we're contracting this muscle and then we'll relax it as that food moves down. And then we pass through this sphincter. That sphincter is called the gastroesophageal sphincter or lower esophageal sphincter. That's another name for it. So that lower esophageal sphincter is the thing that will then open up and so that that food can pass into the stomach. Sometimes this gastroesophageal sphincter or lower esophageal sphincter is sometimes called the cardial sphincter because it's close to the heart. But remember that what's in the stomach is stomach acid. And so if that lower esophageal sphincter isn't really working so well, then some of that stomach acid can go back up into the esophagus. And if it malfunctions, it's kind of like that burning feeling in the esophagus because those stomach acids are really, really acidic. Not super comfortable to regurgitate it a little bit. So, speaking of the stomach, what's going on in here? The stomach is kind of like this J-shaped organ. And so here's our esophagus coming in. There's that cardial sphincter, lower esophageal sphincter, whatever you want to call it. And the first part of the stomach, this guy here, is called the cardia. Then we can see there's this part that goes up that's called the fundus. The fundus of any organ is the base of it. It's usually the farthest away from the opening. So the fundus, I always remember F is for farthest away from the opening. And then the biggest part of the organ, that's called the body. And then there's the pyloric parts. So there's we'll highlight these words for us. There's the pyloric antrum, the pyloric canal, and then lastly, the pyloric sphincter. So the pyloric antrum is kind of like this more like bigger part. The pyloric canal is a little bit of a skinnier part, and then the sphincter is kind of what closes it off before we enter the first part of the small intestine that's called the duodenum. The duodenum is the first part of the SI, small intestine. I think of the pyloric parts of the stomach as kind of like a funnel. Do you see that? Where it's big at the antrum and then it kind of gets skinny, skinny, skinny until we get to the pyloric sphincter, and then all of that stuff passes into the small intestine, which is the next part. The stomach also has some major curvatures. So we have the greater curvature, which is this big curve, and then the lesser curvature, which is the small curve. Hanging off of these curvatures is the omentum of the stomach, which are just special names for mesenteries of the stomach. So off of the greater curvature, we have the greater omentum. And that's just a mesentery. a double layer of peritoneum, serous membrane. And the greater omentum hangs kind of over a lot of the small intestine, kind of like an apron. The lesser curvature hanging off of there is the lesser omentum. Still a mesentery. But the omentum, or the plural of omentum, is omenta, just so you know. But they're not shown in this picture. They're not shown in a lot of pictures, but in a future video, I'll show you some pictures of the mesenteries of the body. The thing to note here is that this is still part of that general tube-like structure. So remember that there's still those same layers. We still have the mucosa layer, we still have the muscularis externa, we still have the serosa, all of the things. So speaking of the muscularis externa, it's an important point I'm going to make, so I'm going to highlight it in blue. So the muscularis externa layer, that's important because in the previous video we talked about the longitudinal layer and we talked about the circular layer. In the stomach, we have one additional layer. It's called the oblique layer. That's the one I'm going to highlight, the oblique layer. Oblique means like diagonal. So notice how the muscle's kind of going obliquely, and then the circular one's going around, and then the longitudinal one is going long ways. You see what I mean? And all of these things work to help the stomach do what it does. And what the stomach does is grind up foodstuffs so that we can digest them. So all of these muscles are able to perform different actions to squeeze and manipulate and grind up that food. So that's the gross anatomy of the stomach. What's actually going on inside that stomach wall? The thing to remember here is that the stomach works to move and mix food, and it does a really good job of grinding up that food into small bits so that we can send it to the small intestine, right? Like through the pyloric sphincter into the small intestine. Remember that inside of the wall of the stomach, so here we are, inside the wall of the stomach, we've enlarged it here. We still have those layers. We still have mucosa. We still have submucosa, muscularis externa with that extra oblique layer. And then we have serosa on the outside, sticking everything to the body wall. Inside the stomach is just the same layers, but there are some modifications, and those modifications help the stomach be really good at doing stomach jobs, which is to create an acidic environment, to do digestion, and make a protective mucus to cover the lining of the stomach because the stomach has some pretty harsh conditions. The mucosal barrier, these modifications help the stomach be really good at doing stomach jobs, which is to create an acidic environment, to do digestion, and to make a protective mucus to cover the lining of the stomach, which helps protect it from the harsh stomach conditions. Those acidic conditions are very, very hard on the tissues. So we need that protective mucus. And so there's lots of cells that do things to secrete that mucus, and it's very, very rich in bicarbonate. Bicarbonate is a base, so that opposes those acidic conditions of the rest of the stomach. I'll talk about all of this. The cells of the stomach are also replaced quickly because of how harsh the conditions are in there. Okay, so jumping into the different cell types, there's a handful of cells that we'll talk about, and all of them help to do the digesting jobs. There's several gland cells that do some functions. So the first that we'll talk about are the parietal cells. So there's parietal cells. So what we're looking at to orient you is we're looking at the mucosa of the stomach that we've enlarged. And then each of these little indentations in that wall are called gastric pits. So each of these gastric pits then leads into like this tubular gland thing. And all of the stuff in that tubular gland thing have different cell types. And one of them are parietal cells. So what parietal cells do is they're found in the gastric glands, which is this part here, gastric gland. That's this part with all the colors. And they make hydrochloric acid, so HCl. They make hydrochloric acid, which is super acidic. Think like pH 1.5 to 3.5. Very, very acidic. Parietal cells also make intrinsic factor, which is helpful for when we get to the intestines for absorbing B vitamins, B12 specifically. So intrinsic factor, that's good for absorbing B12. B12 is really important for erythropoiesis or red blood cell making. So if you hop back to our blood chapter, that's where we talked about vitamin B12. Anyway, so parietal cells, hydrochloric acid, super, super acidic. Many exclamation points, very acidic. And that's really great because it helps do the important thing, which is facilitating the process of digestion in the stomach. Why? Well, I'll get to it because it's the next cell type. The next cell type are chief cells. Chief cells exist also in the gastric glands, but they make a protein called pepsinogen. Pepsinogen. And pepsinogen and hydrochloric acid, they need to work together. So I'm going to scroll down a little bit. So what we're doing here is we're zooming in on this part. So in here, in this zoomed in portion, which is zoomed in of this zoomed in portion of the wall of the stomach, what we see is that we have parietal cells, we have chief cells. When the chief cells make pepsinogen, the hydrochloric acid from parietal cells helps make the enzyme pepsin. What pepsin does? Pepsin is an enzyme that it's an enzyme that digests protein. Digests protein. And this little arrow here is to indicate that pepsin and hydrochloric acid can help make pepsinogen into pepsin. And I always remember what pepsin does because pepsin sounds like peptide, and peptide is like a tiny bit of a protein. Anyway, so what parietal cells and chief cells do is they work together to make pepsinogen into pepsin. Pepsin only works in an acidic environment with hydrochloric acid, so that's really, really important. Chief cells, they also make, which is kind of like a side story, they also make lipases, which is for breaking down fats. They help digest fats, but it's a smaller percentage, like 10 or 15% or so of the fats we digest is from the chief cell lipases. Anyways, lastly are these cells called enteroendocrine cells. Enteroendocrine cells are these guys down here, or these guys down there. Enteroendocrine. Entero means gut. That word entero, let's zoom in there, means gut. Endocrine is secreting stuff into the tissue, but for our purposes, it's hormones. So they make gut hormones. And paracrines is another word for just like cell signaling stuff, but like a local version. These cells make a bunch of stuff. I'll give you some examples. Um, but these hormones are things that can travel through the blood to other digestive organs, but they can also just locally hang out in the stomach. So here's some examples of enteroendocrine hormones, and there's a lot that your book talks about. So there's gastrin, which is a hormone that helps with regulating stomach secretions. Stomach secretions. There's also histamine. We talked about histamine in the immune system lectures because those are like released by basophils, histamines. In the stomach, histamine can stimulate the release of hydrochloric acid from parietal cells. So gastrin, histamine, there's a bunch, but those are just two that are like a good example, I think. So inside of the stomach wall, we have gastric pits. Inside the gastric pits are the glands, and then the glands make things like hydrochloric acid done by the parietal cells, pepsinogen, which then becomes pepsin, the protein digesting thing from the chief cells, and then a bunch of hormones from those enteroendocrine cells. All of these things help regulate or do the processes of digestion. So we mentioned that the mucus layer in the stomach is really important to protecting the actual epithelial lining from getting damaged. But if that mucus barrier gets breached, all of that acid reaches the stomach walls, and that could cause inflammation. And if there's a lot of damage to the tissues of the stomach, that's called an ulcer. So that's what we're looking at here. This is called a gastric ulcer. This side that we're looking at here, that little hole there. So we're literally eating away bits of the stomach wall, which is absolutely not comfortable. And if it's really severe, then this can be a hole in the stomach wall, which is then open to the abdominal cavity, and that's called perforation, and that's no good. Commonly, most ulcers are caused by this bacteria. This bacteria is called H. pylori, which is really good at digesting that stomach wall. So we don't want those bacteria to be causing a lot of damage. A lot of folks have H. pylori swimming around in their gut, and it's not a big deal. It's just when those numbers become abundant enough to cause damage, that's when it's a problem. Typically, a course of antibiotics can do the trick to resolve stomach ulcers, as long as they're caused by those bacteria. So all of that anatomy and all of that histology leads us to what does the stomach actually do? What digestive processes are going on? So there's a lot of events here. But first off is the process of moving stuff, which is propulsion. We move stuff toward the end, propulsion, that's still peristalsis, but we also mechanically break stuff apart by churning actions of the stomach. So that really makes everything move and groove inside of the stomach. But we also do chemical digestion, especially for proteins, by the actions of pepsin. So that's pepsin, and that's for proteins, remember. Um, and by the acidic environment from hydrochloric acid. Most proteins really don't like acid anyways. So when proteins encounter something that they really, really don't like, they kind of start to fall apart. And so since most proteins don't like acid, they start to fall apart in the stomach. And that process is called denaturation. But making the protein less folding, because proteins are usually like folded up little strings, and making it more linear, it makes it a lot easier for digestion and a lot easier for things like pepsin to act on those proteins. But we also have enzymes like renin that helps break down this protein casein. So we do breaks down casein, which is a milk protein. There's not much absorption happening in the stomach. A little bit of stuff happens, like the lipid soluble stuff. And this tends to be stuff like alcohol and stuff like aspirin. Okay, so that's what the stomach does. How are those activities regulated? We aren't always digesting in the stomach or moving stuff forward, so what makes us do those things? One way that we can regulate activities in the stomach is to regulate gastric secretions. So, like how much stuff is being released into the stomach from those gastric glands. And this is done through signaling. And those stimuli can be, or those controls rather, can be neural or they can be hormonal. So, our neural controls are if we're activating the PSNS or the SNS. Remember that the PSNS, the parasympathetic nervous system, is going to increase gastric secretions because we're focusing on resting and digesting. But then the SNS will then downregulate those secretions. But we also have hormonal controls. And those hormonal controls are done mostly by that hormone gastrin. Which motivates hydrochloric acid secretion. Your text also talks about three major phases of gastric secretion and the events that cause or don't cause those gastric secretions. So, the first thing that happens is the cephalic reflex or the cephalic phase. And this cephalic is like referring to the head because it's not even when we've ingested food, it's when we smell food, taste food, see food, or even just think about food, and that sends neural stimuli to the vagus nerve. So this is all like in the head. It's like seeing food, smelling food, thinking about food, and that activates the vagus nerve, which is the PSNS one. And that sends messages to the stomach to get things going. So think about if you think about a food that's really delicious and you kind of start salivating. Um, and then maybe you start feeling a little bit hungry, that kind of thing. But then next is the gastric phase. Gastric refers to stomach, and the gastric phase is when food actually reaches the stomach. So when food enters the stomach, it stretches. So the stomach stretches. And when the stomach stretches or distends, that activates reflexes to tell your brain, like, hey, I have food in here. We need to start digesting it. And there's chemical stimuli there because when you've digested some food, that's going to promote more hydrochloric acid by the actions of gastrin and histamine. And then, of course, we're going to digest those proteins with the help of hydrochloric acid and pepsin and all of the things. Um, but the flip side, so that's when the stomach is full or getting full. The flip side is that if your stomach is empty, it's pretty acidic in there without the food. And when it's pretty acidic, we don't want to make it too acidic in there. And so our gastric secretions when the stomach is empty are minimized. This also happens when you're stressed either physically or mentally. Your SNS, your sympathetic nervous system, is activated. And when the SNS is activated, that oftentimes overrides that PSNS input. And so you're going to focus less on that digestion and minimize those gastric secretions. The intestinal phase is last. So remember, the small intestine comes right after the stomach. right? In our digestive tube. So the intestinal phase, that one's next. And it's really referring to the small intestine. The intestine is receiving the products that the stomach makes, which, by the way, the stomach makes this product called chyme. So the stomach grinds up that food and it makes this stuff called chyme, Chyme. Like food paste is how I think about it. And so that chyme enters the small intestine, um, and that duodenum, that first part of the small intestine, when it gets filled, it releases intestinal gastrin. So when the SI is filled, it releases intestinal gastrin. It's a hormone. It acts on the stomach to keep digesting stuff, but when the small intestine is filled, then the signals shut off. And so we're like, stop producing gastric secretions. We need to slow down digestion because we need to slow down the emptying of the stomach so that the small intestine can catch up. So there's all of these phases. So in the head, we start the process of digestion by like activating our vagus nerve, or not if food is not around. The gastric phase happens in the stomach by how much stretch there is, by how acidic the environment might be, and then the small intestine is also going to provide some input as well. So those gastric secretions are regulated depending on if there's food around and all the things, but gastric motility and emptying of the stomach is also an important thing. So motility is the next point. And emptying, because it really just depends on the amount of food that's present or not present. When the stomach stretches, it's able to maintain the pressure. So stretch is what we're talking about. We need to be able to maintain pressure within the stomach to optimize the churning, the digesting functions, the motility increases. So when there's more stretch, then there's more motility. Because we're trying to create that chyme, right? This stuff, the chyme, the food paste. The actions then of peristalsis, moving in the forward direction, are such that once we get close to the pylorus or the end of the stomach, there's really, really strong contractions there. And they're so strong that some of that food gets kind of pushed back into the stomach, and that also aids in mixing. So again, similar to the above, it depends on the amount of food that's in there that makes the contractions stronger or makes them weaker. But it also happens with what's going on in the duodenum. How full or not full is it? And the duodenum, again, is the first part of the small intestine. If the duodenum is stretched, then gastric emptying will slow. So if the duodenum is stretched, then gastric emptying slows. Which makes sense, right? Because if the small intestine, the thing that's next, is backed up, we don't want to shove more stuff in there. That's just going to make a mess. How quickly or slowly food moves through the stomach also depends on what you eat. So liquids are really quick to move through, solids a little bit slower. So there's a lot that goes into regulating stomach activities. Here's a summary slide for those phases that I talked to you about, the cephalic phase, the gastric phase, the intestinal phase. Note that there's some brain talk here and reflex talk here, but I still think this is a really, really good slide because you can look at what stimulates motility and all of the things, and then what inhibits all of those activities. This is the last slide we have here. This image is showing those peristaltic contractions for the stomach. So here you see how propulsion works. So we're contracting the stomach, moving that chyme, that food forward. And then we have those grinding actions. The grinding actions is lots of peristalsis, lots of mixing, and that pylorus is closed, that pyloric valve. And there's that word again, chyme. And then the last part is retropulsion. That's a new word, so I'm highlighting it. So it's when we push that food forward, but that force is so strong that some of it kind of hits that valve as it closes and it comes right back, which aids in mixing. That's where I'm going to end this video. We'll come back for the rest of the major digestive organs.